What is the analytic at x0 means? We record this concept. So P and Q, a function is analytic at this point means that the function can be expressed by a power series over this point. That is, the function has infinitely many differentiability. It can be differentiated infinitely many times. Therefore, we can construct its Taylor series, and the sum of the Taylor series equals the function identically in the neighborhood of x0. So this is what analytic means. This is a concept we have introduced at the beginning of today's lecture. Okay. Now, so if the small p and the small q are analytic at x0, we say that x0 is an ordinary point of this capital PQR equation. Okay. The concept of ordinary point we have mentioned at the beginning of this lecture, but at the time we assume that PQR are polynomials. For polynomials PQR, if Px0 is not 0, then x0 is ordinary point. Now we generalize the concept of ordinary point slightly. So our capital P, capital Q, capital R are not need to be polynomials. But for that is the PQR can be more general functions. But if the quotient of capital Q over P and the capital R over P are analytic at x0, we say that x0 is ordinary point. This is a generalization of our previous concept of ordinary point. Okay, and if x0 is not an ordinary point, we say that it is a singular point. Okay, so this is a definition of the general ordinary point and a singular point. Okay. Now, using this concept, we have this theorem. Suppose x0 is an ordinary point of this variable coefficient linear ordinary differential equation. Then, the general solution of this equation is analytic, and that is, it can be written as a power series. And this power series can be split into the sum of two power series, y1, y2. Here, y1, y2 are also power series solution of the same equation. Okay. In fact, they are from a fundamental set of solution. Therefore, a1 and a2, maybe I will write here a0. Maybe that's okay. Our a1, maybe I will write c1 and c2. This a1 is not the first coefficient of this power series. Okay, so this is another two. These are another two misprint. Okay, so this y1 and y2 are power series solution of the same equation, and they are also analytic at x0 and form a fundamental set of solution. So this theorem. This part of this theorem ensures that about an ordinary point, the solution of the second order equation can be expressed by power series. Okay. Now, how large is the radius of convergence of this power series? So the second part of this theorem says that the radius of convergence for y1 and y2 is not less than the minimum of the radius of convergence of these two analytic functions. Our assumption is that small p and small q are analytic. Why they are analytic? Because x0 is an ordinary point. X0 is an ordinary point by definition, which means that small p and small q are analytic at x0. In other words, small p and small q can be expressed by a power series about x0. So as they can express by power series, they have the corresponding radius of convergence. For P we have a radius of convergence rho 1. For Q we have another radius of convergence rho 2. So this part of the conclusion of the theorem says that the radius of convergence of y1 and y2 is not less than the minimum of rho 1 and rho 2. Okay, so this is very useful. Without obtaining the coefficient an here for the solution, we can obtain the lower bound of the radius of convergence for power series solution. So this is very useful, a very useful conclusion. And also, we emphasize that this lower bound of radius of convergence does not depend on the concrete, explicit expression for the power series solution. That is, we don't need the explicit expression of the coefficients of the solution. Okay, and but for general analytic functions small p and small q, the radius of convergence might not be easy to compute. Why? Because you need to compute the quotient q over p, capital Q over capital P, and then you need to expand this quotient function into a power series, and the coefficient of the power series should be able to express explicitly so that you can determine the radius of convergence for small p and small q. That is not easy. Okay, that is not easy as well. Okay, but if the capital PQR are all polynomials, that is from complex analysis, we know that the quotient of two polynomial, that is capital F and capital P are polynomial, and capital P x0 is not 0, then the quotient function, that is a rational function, has a power series expansion about x0. Okay. And also, the radius of convergence of this, quotient function is precisely the distance from x0 to the nearest 0 of the denominator capital P. So, in the special case when capital P, Q, R are all polynomials, we can use this remark to obtain the radius of convergence for the power series expansion of the small p and the small q. Because when capital P, Q, R are polynomials, the small p and the small q, for the small p and the small q, we can use this remark to obtain the radius of convergence. So we consider some example. Suppose phi is a solution of this variable coefficient second order linear equation, which the initial value condition y0 is 0, y prime 0 is 1. So we are required to compute the first several derivative of phi at 0. Okay. Now, from the equation, because phi is a solution of the equation, we can replace the unknown function y by phi here, and then we evaluate the resulting equality at x equal to 0. We obtained 1 plus 0 square phi double prime 0 plus 2 0 phi prime 0 plus 4 0 square phi 0 is 0. Okay. Then from this equality, we can solve for phi double prime 0, which is 0. Okay, so we have already determined the phi double prime 0. So to obtain the triple prime 0, the third order derivative, because the equation only contains the second order derivative, we need to differentiating the equation first to obtain the y triple prime, and then replace the y by the solution phi, and then evaluated at x equal to 0. Okay, so differentiating the equation, so the derivative of this is 1 plus x squared y triple prime, that is phi triple prime, plus the derivative of 1x squared, 1 plus x squared, multiply y double prime, that is 2x. The derivative of 1 plus x squared is 2x. So this is 2x phi double prime. So the derivative of the first term in the equation is this, the sum of these two terms. And the next we derivated this. So this is 2y prime plus 2x y double prime. Okay? And now this term. This term is 4x squared y prime plus the derivative of 4x squared, that is 8x, then y. So differentiating the equation, we get this equality. Now evaluating this equality at x equal to 0, we obtained the first term is phi triple prime 0. So because we are evaluating at x equal to 0, those terms containing a factor x, this term, and the last two terms are all 0. Only this 2 phi prime term remains. So we have obtained phi triple prime 0 plus 2 phi prime 0 is 0. And the phi prime 0, because phi is the solution of this initial value problem, so phi prime 0 is 1. So we conclude that phi triple prime 0 is the inverse of 2 phi prime 0, that is minus 2. Okay, so we computed the phi triple prime. Okay, so to compute the first order derivative, the equation does not contain the first order derivative. The derivative, the differentiating equality we obtained is also not contain the first order derivative. So we need to differentiating this equality one more time to obtain the first order derivative, and then evaluating at x equal to 0. Then we can obtain an equality containing phi, the first order derivative of phi at 0. But to save time, I will not perform such computation anymore. But that is easy and in some sense stupid computation. Okay. Now we consider the next example. We have a function capital small p, which is a rational function. We are required to determine the radius of convergence of the Taylor series for this rational function about x equal to 0. So how to solve this problem? We use the remark we just mentioned. Okay, because this p is capital F divided by capital P. So the first step, we need to find the zeros of the denominator, that is capital P. It is easy to see that the zero of capital P, that is the denominator, is 1 plus and 1 minus I. Okay. Then by our remark we just mentioned, the Taylor series of this function about x equal to 0 has radius of convergence equal to the nearest 0 of capital P, the distance from the nearest 0 of capital P to x equal to 0. So both 1 plus I and 1 minus I has the same distance to x equal to 0 in our example. This example. Therefore, the radius of convergence of the corresponding power series. So this power series is x minus 0 to the power n. So this is the power series about x equal to 0. Okay. So the radius of convergence of this power series is the nearest, is the distance from 0 to the nearest 0. But x equal to 0 to both zeros of capital P are the same. The zeros of P are 1 plus I and 1 minus I. So the distance is the norm of this complex number. That is 1 plus the norm of 1 plus I. That is square root of 2. So this is the radius of convergence for the Taylor series about x equal to 0. Similarly, for the Taylor series about x equal to 1, then the series should be Bn x minus 1n x minus x0 to the power n. The x0 is the point you are expanding. So the Taylor series about x equal to 1 is the series of x minus 1 to the power n. So the radius of convergence by the Stanley mark, the radius of convergence of this power series is the distance from 1 to the nearest zeros of capital P, but 1 to both zeros of capital P, that is 1 plus I and 1 minus I, are the same. The distance is 1. So the radius of convergence is 1 for this case, for the Taylor series about x equal to 1. Okay. Now our final result, final example, we have a second order linear equation. So we are requiring to determine a lower bound for the radius of convergence for the series solution for this equation about the point x equal to 0 and x equal to minus half. Okay. So the capital P is 1 plus x squared. So the zeros of capital P is r equal to positive or negative I. So for the power series solution about x equal to 0, so the radius of convergence is not less than the distance from x equal to 0 to the nearest 0, but x equal to 0 to both zeros of capital P, that is I and minus I, the distance is 1. So the series solution, assuming that it is of this form, the coefficient is an. We don't care about the expression for an. We don't need the expression of an. But we know that this series, the radius of convergence is at least 1. So this series converge at least for minus 1 to 1. X, the absolute value of x less than 1, which means the open interval minus 1 and 1. Similarly, for the power series solution about x equal to minus a half, so we need to the radius of convergence is not less than the distance from minus a half to the nearest 0 of P, but the distance from minus a half to both zeros of this capital P is positive or negative I plus a half. So this distance is the square root of 1 square plus a half, the square of a half. That is 2 over square root of 5 over 2. So this means that the series solution about x equal to minus a half will converge. The radius of convergence is at least square root of 5 over 2. That is when x minus a half, that is x plus a half, the absolute value less than square root of 5 over 2, then this series solution converge. Okay, that is the series solution. The series solution is defined and converge at least in this open interval. Okay.